Okay, so curl and divergence. So this is actually a pretty interesting topic and very theoretical, and it's actually interesting how it actually plays out in life. So before we go actually into the actual section, let's do a quick review of what it means to be a vector field. So a couple sections ago, we went through how to draw vector fields in space, and those are, I'm sure, were pretty difficult to deal with, but doable, right? So here we have three vector fields. Okay? And I hinted in that section as well. Notice they follow a nice little pattern, right? So like, for example, if I follow these arrows, you can kind of tell they all show you kind of like a curve they follow or a path. Okay? Same thing applies to the other ones, right? Notice that we have like this way or that way, these waves going in that direction. And also applies here. So this like curvature, this one's going outward here. So it looks like kind of like inward, starting from the center and going outward, which is pretty cool. Now, these right here is what we're going to be talking about first. Those are called curls or paths in vector fields. So a vector field itself ends up giving you another vector itself. And that's what we're going to talk, or that's what the curl is actually going to be. So as you can see, there's a path or curl within the vector, and this is what we're going to talk about. So now, how do we find the curl itself? And the curl is actually pretty straightforward, which is nice to find. It's something we've already done. So let F be a vector field in R3, and the partial derivatives exist. So therefore, the curl of F, or the curl of the vector field, is defined by this. Okay. Now, you may think that's a pretty hard to memorize. Well, or just to understand itself. So let's go. Now, we're going to go back to this, right? So remember that symbol represented the gradient, right? So the gradient of a vector field or gradient of a vector. Okay? So the easier way to remember is the curl of F is actually the gradient with the cross product of the vector field. Okay? Which is much easier to see what's going on, right, when it comes to it. So now, how do we prove this? Right, we haven't done any proofs in a while. This one's actually pretty straightforward to show. So we want to prove the gradient cross product of the vector field equals a curl of F, meaning we get this back itself. Okay. Now, so if you guys remember, cross product means this stuff here. It's been a while. So the gradient is just the derivative with respect to x, respect to y, and respect to z. And then this one, we're going to let F equal exactly that. So P, Q, and R. So therefore, if we do this process, right? So here's the ith component. So it's going to be this times this. So the derivative with respect to y of this. So it's going to be dr dy minus this times this. So the derivative of q with respect to z. This is the ith component. Minus same thing on the other side. So jth, you cross out this one. So it's going to be this times this. Minus that times that. And then finally, plus the kth component. So get rid of this column, that times that, minus that times that. Well, if you notice, that's exactly what we want. So therefore, this is the curl of F. So, which is much easier to deal with than having to memorize what goes where, right? All we have to do is the cross product, and it guarantees it's a curl there. Okay. So let's try some out. So simple little example, let's find the curl of this vector field f of this. So therefore with the curl, we just proved it right, of f is equal to the cross product of the gradient times f. So in this case, it's going to equal to and then we do f. So xy, xyz, and then minus xy squared as our p, q, and r. Okay. And then we just follow the template. So for I, it's going to be, get rid of this times this. So we're going to take the partial derivative with respect to y. That's going to be negative 2yx minus the partial derivative with respect to z, which is going to be xy, I, minus, then we do the jth. So that's the middle term goes away. So the partial derivative with respect to x over here is just going to be negative y squared minus the partial derivative with respect to z is going to be 0. And then lastly, the kth component. So it's just going to be this 4 here. So partial derivative with respect to x, and then partial derivative with respect to y. And there we go. So then simplifying this a little bit, right? We could put this together. So it gives us negative 3 xy. And then I could distribute this negative on the inside. Which is going to be y squared. This is 0. So that's j. And then this is going to be by itself. There we go. And that's how we find the curl of a vector. Now, one quick note before we go any further of this curvature. The funny thing is, remember the gradient of f, right? So given the original function f, if we find the gradient of it, that's defined to be a vector field. Okay? Which means we could find the curvature of any vector field. So we could find the curl of the gradient of f. Now, this is actually very important because it actually connects gradient, curl, and conservative, meaning a conservative vector field. Okay, so if f is a function in 3 variables, therefore, this will be true. The curl of its gradient will actually equal 0. Now, if we know f, the vector f is a conservative vector field, we know that f is equal to the gradient of f, right, by definition of being conservative. So put in these two definitions together, we get a very special theorem that f is conservative vector field if and only if the curl of f equals 0. So that's an alternative way to find if a vector field is conservative or not, just by using this curl now, right? There was a couple of things we could have done last couple sections. This one now gives us the curl, which sometimes a little easier to deal with, right? Straightforward, just do the cross product and see does it give you 0 or not. So for example, is the vector field of the one we did earlier conservative or not? So we found no, right? That's not equal 0, so this will be a no. And that's how easy the check would actually be. So just fun little interesting portion connecting all 3 together. You'll see that later on when we do Stokes theorem, what connects 4 of the major topics into one simple integral, which is pretty crazy when it comes to it. But for now, let's just do a couple more examples. So the first question is the vector field a conservative vector field? So is this if, and I forgot to bold this for you guys. So I'll just put the arrow on top. So is this vector field a conservative vector field? So all we have to do is check. Does the curl give me 0? So we'll just quickly do that. So let's find the curl of this vector field. We'll run out of space here. There we go. All right, and we do the same thing we just did on top. All right, so blocking out the i's. So the derivative with respect to y in this case, so we'll have to look up here. Derivative with respect to y is just going to be 6x squared y minus derivative with respect to z, which is going to be 2xy. So that's the ith component. Oh, it's a cube. That's a 6 then. Oh, it's a z2. Too many, I put too many letters in this example. So up here. Okay. All right, minus j. So derivative with respect to x. So this with respect to x is just going to be itself with no x involved. Minus derivative with respect to z. So that's going to be 3z squared y squared. Just j. And then, okay. So take this off. So this one, with respect to x, is just a self-defined x. Minus with respect to y. So this is going to be 2y z to the third. Okay. All right. So now we just check, does it give you 0? That's all we have to do. All right. So let's see what we have here. So 6, you got an x, you got a z squared. Oh, this actually gives you 0. One down. 3 z squared y squared also gives you 0. On a roll. And the last one. 2 y. Oh, perfect. So we get zeros. So therefore, this is a yes. So yes, it is a conservative vector field. So therefore, because it's a conservative vector field, we can use its second part. Then find f such that f is the gradient of f. So we did a couple examples of this, not too much thoroughly. Remember, all you really have to do is integrate each one individually and see what they have in common. So for example, we're going to integrate the first one, the ith component, with respect to x. So this gives me just x times all of this, plus some c term. Integrate the second component in terms of y. So notice if we take the integral of this one, this ends up being same thing on top because then y becomes squared plus c. And the last one with respect to z. And again, notice this ends up being the same thing because if we put the 3 up top, we have z to the third plus c. So notice they all have the same one in common. So it looks like our function in terms of x, y, and z is just going to be x, y squared, z to the third, plus some constant. Okay. Now again, that constant could be anything you want. Now most of the time, we'll just let c equal 0. So your function just be that. Because again, 0 is a constant, right? Itself. Especially when we do, if I ask you what's the function of f at the point 1, 1, 1, you would just put c equaling 0, and then you would plug in 1, 1, 1 in for x, y, and z. Okay. Any questions so far? Good. So far, so good. Okay. All right. So let's go back to this portion of vector fields, okay, and some curls. So I talked about what a curl means, right? So for example, here, right, we can show what the curl would look like, maybe. How would it look like? That's a nice thing. Okay. Now, so this is a curl. The curl of, let's say, some function vector field. All right. Now, what we're going to do is, let's suppose we're given an arbitrary point on this curl. Let's suppose this point right here. So this is my point P. No, so some random point on there. Okay. Now, at that point P, what we're going to do is we're going to make a circle that's centered at that point. So let's just make a little circle that's centered at that point. So what we're going to do now is I can measure how much the flow is expanding at that point. What I mean by flow expanding is, okay, how much is the flow going this direction or that direction? No, now the orientation is not going to be important, but how much is it going inward or outward, at that point? So we can see how fast it's going, right? So remember, these vector fields get longer and shorter, right? But at this particular point, if I make a circle, I could see how fast it's going this way, how fast it's going that way, and vice versa. It's just, how the rate of change of the flow, okay? Now, that is what's called the divergence of a vector field. Okay. Now, here's the problem of this divergence. This does not tell me in what direction the flow is going. So that's we'll talk about that later on, but for now, we could find the actual flow. So again, I don't know if it's the fastest flow is this way, that way, this way, but it tells me how much the rate is going expanding in that direction or in some direction itself, okay? So that is what really the divergence of a vector is actually all about, okay? So, and that leads off to our next example or definition. So let F be a vector field in R3, and again, the partial derivatives exist. Then the divergence of F is given by this function here. Now, the cool thing is a scalar multiple, so it's an actual flow, right? It's like a rate of change. It gives me a number out. Okay? Unlike the curl, which gives me a vector, divergence gives me a value out. That's a key component itself. I'm going to talk about that later on as well. So the easiest to remember is the divergence is the dot product, while the curl is the cross product. Crazy, huh? First day of class comes back to, one of the last days of class, cross product and dot product. Now, the key thing is when it comes to the curl and the divergence is the order in which they do does actually matter. Meaning, if you do it this way, it's going to change up. That's actually defined to be something else. Same thing if you do the other way. Well, I guess this one doesn't matter, but this one really doesn't matter. Okay. So it's always the gradient dot across the F value, the vector field. So just be careful how you order stuff. That was one of the biggest things on the test as well. So in that case, well, we'll try using the divergence to see how one is related to the other. Okay, so let F be a vector field, find the divergence of F. So now we're just going to do the dot product instead of the vector of the cross product. So remember, how do we do dot product? It's much easier than the cross product, right? So the divergence of F is going to be the vector of the gradient with the vector field. So in vector format, it's just going to look like this. Like that. And now how, remember, dot product works is we do this multiplication, that multiplication, and just add them all together. So for example, here we take the derivative with respect to x. We're just going to add the results of each one itself. This one, we're going to take the derivative with respect to y. And the last one, derivative with respect to z. So our divergence is y plus x z. And if we had a point, for example, at the point, again, 1, 1, 1, we would plug in 1, 1, 1, and we get the scalar itself. So that's the exact flow, or how the flow is expanding at that point. So the last part of this section is how do things come into play all together? So what I mean by that is, again, going back to vector fields and more importantly, Green's theorem, how does everything flow with one to each other? Okay. So we can actually rewrite Green's theorem using curls and divergence of a vector field. So remember, the Green's theorem stated that the line integral, there's another alternative way using the line integral, right? However, when it comes to the curl and the divergence, is a line integral can actually be represented as the curl of a vector field over a region D. And this region D is literally just a box, which is nice, right? It's easier to do X and Y. Okay? So this integral is the integral over the region of the curl of F times K, where the K is the kth component of it, dA. Okay? Or if we use divergence portion, where N is a unit normal vector field, right? This is the alternative way of writing the curl, not the curl, the line integral. So the alternative way is equal to the double integral over a region D of the divergence of F dA. In this case, where N is the unit normal vector of C, depending on what we're actually asked to find. Okay. So remember, line integrals are pretty painful to deal with, manually. You had to, parameterize the vector field and then do all this fun stuff. The question now is, what Green's theorems is and what the curl does is alternative, easier ways to find the line integral of some stuff, right? Because it's much easier to deal with than have to do, all this fun stuff. And same thing over here, where you have to find the normal unit vector and all that horribleness. Just find the divergence and just integrate over the region of D. All right, so let's prove this stuff. And these proofs aren't too difficult, which is nice. Okay. So let's prove the first one, and then we'll prove the second one. So proof of one. So the proof of one is we're going to show this is true. Okay. Okay. So let's say given F being a vector field that's equal to this. And we have a line integral. And that line integral is equal to this. By definition, according to Green's theorem, could equal this. Okay, so we're going to show, going backwards, because line integral from here is too difficult. We're going to show that the curl of F actually gives you the line integral. We're going to go backwards. So we're going to show this actually equals that. Okay. The other way is much harder to deal with. Okay. So that means first we find the curl of f. Again, we've been doing that. That's just the gradient time cross product the vector. So that's going to be I, J, and K. It's bad J. So P, Q, and R. Now, this is the interesting part. Remember, our vector field, it's only in terms of X and Y. Because we don't know, we don't have an rth component, right? It's just I, J, and K. There's no K there. So remembering that when we do our derivatives, right? We get rid of the i's. It's going to be, oh, actually, this is 0, sorry. There's no K. The derivative of respect to y is just going to be 0 because it's 0. Now this one is only in terms of X and Y. So what's the derivative of, in terms of Z, is also going to be 0. Okay, so J, this with respect to X is going to be 0 because it's 0, 0. And again, this is in terms of just X and Y. So therefore, the derivative with respect to Z is also going to be 0 because there's no Z's. So I and J are pretty much gone. And then the final one is K. And that's the only one that really actually works out, because if we do this with respect to X, we actually get something. So that's going to be dq dx minus with respect to Y. Again, we actually get something out. Sorry. This is Y. And this is K. So our curl is just equal to this. Okay. Now, some people want to integrate something, right? And we, this is a vector field. So the only way we convert is, we actually have to get a value out, right? We can't have just a vector itself. So we have to get rid of this component of K. Okay. So to do so, we're going to make the dot product. So we're going to multiply the curl of F which is equal to just this. Right, in the K component. And we're going to dot product with K. Like that. So what this ends up being is these cancel, and we just get this. Well, remember, isn't that just what we get here? Right, remember what Green theorem says, this is the same thing as equaling the integral of this over that, and or the partial derivatives with respect to each other. Well, that's all we just found here. So if we just take the integral of both sides, we get exactly what we want. If we take the integral of the curl of F times K dA over some region, that's what Green's theorem ended up giving us. This is actually a line integral. So therefore, we're done. Okay. Now this one's kind of straightforward because it just follows definition after definition, or what the manipulations are of each respective line integral. The other one's a little trickier to deal with. to deal. If you didn't know this trick, you may have just to Google it or something like that. It's just a nice little trick to do with it. However, when it comes to showing that the divergence of it equals the line integral of it, we're actually going to go the opposite direction. Okay, so we're going to start with some curve. Let's say given a curve C by a vector. Where T is in between A and B. Okay. So remember the unit tangent vector is equal to this. I'll separate each individual ones. J, and this is K, I and J. Like that. Okay. Or we could just factor this out, which would probably be a little nicer to deal with. I'll do that right now. Okay. Now, that's a unit tangent vector. The unit vector, or the unit normal vector, had a different equation. This was equal to this. All right. So now what we're going to do is going to put these two things together somehow. Okay. So we know another way to write this. So if I just now, according to one of our definitions, I forgot which definition this was, it equal to this part. Gives us that. Okay, so now all we're going to do is plug in what we know. Okay. So this is the dot product of F, is what we have up here, times the normal vector, which is right here. Okay. And on the outside, it's going to be this. Okay. So we're going to have now integral from A to B of the dot product, so it would just be P times this. So it'd be P y prime of T all over all of this. Minus Q times this. With this on the outside, dt. Okay. Now, you guys all agree these cancel, right? Because if I distribute this to each one, those are the lengths of R primes cancel out completely. And we're just left with the integral from A to B of Py prime minus Qx prime. Okay. So instead of this y prime stuff, this is now just p dy, because that's the same thing as y prime, just dy. Instead of x prime, I'll just put dx. Okay. So now, according to Green's theorem, this is the same thing as finding the double integral over a region of dp over dx plus, because if you swap it because of the minus, dq over dy dA. But what's the definition of divergence? That's exactly what we have. So this right here ends up being the divergence of F. And there we go. Pretty interesting, huh? I know this is a lengthy proof, and we haven't gotten proofs too much in detail in this class, but this is one I really actually want to go over, show you guys.